Hello class, welcome to the channel and welcome to this playlist in which we are discussing about the transformations for signals and systems which helps us to move from time domain to frequency domain or frequency domain to time domain, such as the Fourier transform, the Laplace transform, the Z transform, etc. So initially we started with Fourier series and what is Fourier series, and then later on we saw a little bit detailed view. We had a little bit detailed view of Fourier transform. After that, we also discussed and proved different properties of Fourier transform, and now we are going to discuss about the Fourier transform of a periodic signal. Okay, so uh, if you are following this playlist for a long time, I'm pretty much sure that you have an idea what is a periodic signal. Although if you are totally new at this and if you are living under the rock, you can check out the playlist in which we have discussed about the periodic signals and different types of signals. Basically, we discussed about all the types of signals. We classified all the types of signals uh, with its different classification things. Like we have first classified for CT and DT, continuous time and discrete time, then periodic, non-periodic, analog, digital, even, odd, uh, deterministic and random, absolutely integratable and non-integratable, uh, power and energy signals. So we saw all that classification. So if you want to find a Fourier transform of a periodic signal, how you can find it? Okay, so okay, before we move further, you can check that out. Check out the first playlist in which we discussed about the Fourier transform, and you can check out the older playlist in which we discussed about the classification of signals. In that you will find periodic signal as well. So the link will be flashing on the top right hand side corner of your screen. Click on it and watch it if you don't have idea, and if you already have an idea, moving further, let's discuss what is a Fourier transform of periodic signal. So giving a small glimpse of periodic signal, a periodic signal is a signal that repeats itself after a certain time period. We call the time period T. So it will form a cycle after completing a certain time period. It will repeat itself, and we call that signal a periodic signal. And sine wave or cos wave, both are typical examples of my periodic signals. So you might already have an idea of it, that my sine wave and cosine wave are periodic signals because they are repeating after a certain time period, whereas an exponential signal is not a periodic signal. Okay, it is a non-periodic signal because it never repeats itself after a certain amount of time. And now, why am I saying this? Because when we take the Fourier transform, remember what do? We take e raised to j k omega 0 into t in consideration. That means we are taking an exponential function, and exponential function itself is not a periodic signal in itself, but we can take a Fourier transform of a periodic signal, and by when we take a Fourier transform, we basically are multiplying it with exponential function, but it will help us find the Fourier transform. So how? So let's see. So firstly, let's consider a signal. Wait a minute, let give me a time of a second. Okay, now fine. So let's consider a signal x of t to be periodic with a time period t0. I've already told you what is the time period t0. It is the period after that signal will start repeating itself. So you can represent that signal with a Fourier series, and what will be that Fourier series? So Fourier series will be x of t is equals to summation of k is equals to minus infinity to infinity x of k e raised to j k omega 0 t. Okay, and omega 0, what is the value of omega 0? So it is value of omega 0 is again same 2 pi f, or if you want to find the value of same in the time with the help in the time period, with considering time period, so you can write omega 0 is equals to 2 pi by t 0, or you can also write omega 0 is equals to 2 pi f. So again come back to this signal. We just took the Fourier series of my x of t. Now what will happen when we take the Fourier transform on both of the side? Now you know x of t will become x of omega, but what will happen to this Fourier series? So we will be taking Fourier transform, so it will look something like this, right? We are taking Fourier transform, so f of summation k is equals to minus infinity to infinity x of k e raised to j k omega 0 into t. And remember in the very last lecture we discussed about the linearity property. In that what was happening, uh, we can represent our we can represent our constant, and we can take it outside the bracket. So we did it. We discussed about how your formula needs to satisfy the superposition theorem as well in the very last lecture itself. So using the linearity property, you can write for this formula the same way. You can take f out of the bracket, or you can take rather you can take f inside of your bracket after the sigma, and you can write the formula this way, that x of omega will become summation of k is equals to minus infinity to infinity x of k f of e raised to j k omega 0 into t. Now because you know that x of k is independent of your t, right, it has nothing to do with t to begin with, because t is neither added or subtracted from the signal, and t is also not having any kind of power relation with that signal. So x of k is completely independent of t. So remember that. And now let's see one thing. What will can you tell me what will happen when I take Fourier transform of the number 1, right? When we discussed about the phase shift property, frequency shift property to be precise, we saw that uh, we saw something like this. Let's get back to it so that you can understand it a little bit better way. You can understand it in a little better way. So here we have it. Now this is time difference. Here we have it. So what does frequency shift property says? If you are having a signal which is x of t multiplied with ej beta t e raised to j beta t, so you can take the Fourier transform and it will look like x of omega minus beta. So same thing will happen here as well. So again come here and see, same thing will happen. The value of uh, the Fourier transform of 1 will be 2 pi delta omega. Remember, whenever you take Fourier transform of 1, it will be in the form of its Fourier transform will be in the form of impulse, so you will get 2 pi delta omega. And now considering the frequency shift property, what will happen? This if we take multiplication of 1 into e raised to j k omega 0 t, which is the term present here, what will be the Fourier transform of 1 into e raised to j k omega 0 into t? So it will be considering this Fourier this frequency shift property, it will be 2 pi delta omega minus k omega 0, right? And now what we will do, we will simply substitute the value we just found in the equation of x of omega, or the Fourier transform of x. So we will get summation k is equals to minus infinity to infinity x of k 2 pi delta omega k minus omega 0. Okay, and we can take this 2 pi outside of the summation mark sigma, and you can write it this way as well. So the heart of the statement will remain same, that x of omega for Fourier transform of my periodic signal, x of omega will be 2 pi summation k is equals to minus infinity to infinity x of k into del omega minus k omega 0. That is the condition, or rather Fourier transform equation for my periodic signal. Now there is a property or theorem called modulation theorem, or we saw the modulation property earlier. So now let's say what does modulation theorem has to tell us. So it says when the modulating signal, my x of t is my modulating signal, it will modulate the high frequency carriers such as cos omega 0 t, then the frequency domain representation can be given using this mathematical formula. Okay, so modulating signal x of t is modulating the high frequency carrier like cos omega 0 t plus phi. So the frequency domain representation will be something like this, like this, x of t into cos omega 0 t plus phi, and whenever you took the Fourier transform of it, you will get this term. This term is not very new to us because we are already familiar with the this term e raised to j phi and its relation with sine and cosine and sine. So what you will get e raised to j phi divided by 2 x omega minus omega 0 plus e raised to minus j phi divided by 2 x omega plus omega 0. Okay, and if you want to write it if you want to write it cumulatively, you can write it as well. You can take 2 as the you can send the 2 in the denominator. It was already in denominator, but you can as it is distributed right now, you can take it as a denominator of the whole term. So your f will be your f of x of t into cosine of omega 0 t plus phi will be, so basically the Fourier transform of your signal will be f of x of t into e raised to j omega 0 t plus j phi plus e raised to minus j omega t minus j phi divided by 2. So what you will get a term something like this, f of e j omega e raised to j phi divided by 2 x of t e raised to j omega 0 t plus e raised to minus j phi divided by 2 x of t e raised to minus j omega 0 omega 0 into t. Right, so nothing new here again. We are simply what we are doing, we are simply separating these terms, right, j phi and j omega 0 t, and from this you can write this way, because you can take e raised to j phi by 2 common, and the rest of the term will be f of x of t into e raised to j omega 0 t plus, again you can take e raised to minus j phi by 2 common, and the term will be x of t into e raised to minus j omega 0 t, right. And whenever you phase shift this term, what you will get e raised to j phi by 2 x into omega minus omega 0. So basically you perform the Fourier transform, and you will get x of omega plus omega 0 on the other side, and the e raised to minus j phi by 2 will remain as it is. So that is your modulation theorem, right. Now the third one is the inverse Fourier transform. We discussed about it earlier as well, so again I will give you a small quick glimpse of it. So we can convert our frequency domain signal back into the time domain signal using this inverse Fourier transform. So how can we do it? So we can take the help from partial fraction expression. I'm pretty much sure those who have taken the calculus classes and stayed with calculus for a long time, they are familiar with partial fraction expressions. So you can represent the x of omega using partial fraction representations or partial fraction expressions as 1 by a1 plus j omega plus 1 by a2 plus j omega plus 1 by a3 plus j omega up to 1 by ak plus j omega square. Now if I want to find the inverse Fourier transform of my signal, I can what do I need to do? I can find the standard Fourier transform in pairs. And how? So I will do something like this. This is my time domain signal and I'm converting it in frequency domain. So u of t is my unit step signal, and we already know what is the Fourier transform of my u of t, right? We discussed it yesterday. Now what will be the Fourier transform? Now u of t is multiplied with e raised to minus at, right? So when we take Fourier transform of this term, we will get 1 upon a plus j omega. Now this is this term 1 upon a plus j omega is in the frequency term. So if I want to get back my time domain, what do I need to do? I can do inverse Fourier transform, and when I do inverse Fourier transform, I will get this term back. And about the pair, uh, what it is saying that we can find the inverse Fourier transform with the help of standard Fourier transform pairs. So this is the pair, this one and this one, because what is the Fourier transform of t into e raised to minus at into u of t? So these two terms are equal. The only thing got added here is t, and because of t we are getting square in the denominator of Fourier transform of my term. So that is the difference that Fourier transform can make, and these are the pairs from which we can determine the inverse Fourier transform of uh, so many signals. So that was the Fourier transform part. Now let's move forward and let's see what is a Laplace transform and what is the definition of my Laplace transform. So basically again, Laplace transform is nothing new. It is basically a signal, and you can convert again the time domain into frequency domain using this formula. X of s equals to, you take integration minus infinity to infinity your signal of which you want to take the Laplace transform, which is, let's say, is x of t here. So x of t into e raised to minus st into dt. Okay, and the new term which you will see here, because you will see that Laplace transform holds so much resemblance with Fourier transform. The new term which you are witnessing here is this s. Rest of the terms are a little bit similar compared to the Fourier transform. So this s is an independent complex variable. By mean complex, yes, I mean a plus ib or j plus sorry I plus jb. So here we represent this s with help of this formula. S is equals to sigma plus j omega. And what is the sigma? So sigma is the real part of my signal s, and omega is the imaginary part of my signal s, right? So this sigma is called the attenuation constant, and this omega is called the complex frequency of my signal. So up till now you must have figured it out that this is a bilateral or double-sided Laplace transform, right? So if you take the Laplace transform, you can also find the inverse Laplace transform of your signal. So Laplace transform helps you move from time domain to frequency domain, and inverse Laplace helps you to do the reverse operation of the same, right? So there is something called unilateral Laplace transform. And how do we find the unilateral Laplace transform? So we will change a small thing. Instead of taking integration from minus infinity to infinity, we will change its limit from 0 to infinity. And when we do that, the Laplace transform which we will find will be called unilateral Laplace transform. Now this Laplace transform is mainly used for causal signals most of the times. So the lower limit will be 0 here. Makes sense? Remember what was the causal signal we discussed in the very first playlist? So again, a reminder, if you haven't checked it out, you can check the playlist out. Now the thing which I was discussing, that Laplace transform is mainly focusing on causal signals. So the lower limit is 0. Okay. So we can find the inverse Laplace transform of my signal which is uh, having value in time in frequency domain. You can represent it this way: x of t is equals to 1 by 2 pi j integration sigma minus j infinity plus sigma plus j infinity x of s e raised to st into ds. Now what will you do if you want to converge your Laplace transform, right? You want to make sure that your Laplace transform converges. So earlier also I have told you that Laplace transform holds so much resemblance with Fourier transform, and the reason has been written over here, that Laplace transform is basically the Fourier transform of x of t e raised to minus delta t. So it is basically a Fourier transform, and that's why it is holding so much resemblance with Fourier transform. So if the Fourier transform of my term x of t e raised to minus delta t, or whatever term you want to find the Laplace transform of, if there is a Fourier transform present for it, then you can definitely find the Laplace transform for the same term. So if the Fourier transform of my signal exists, then the Laplace transform definitely will exist. And what was the remember what was the condition for a Fourier transform to exist? That your signal must be absolutely integratable signal, right? It must be absolutely integratable signal, which means it should be BIBO signal, bounded input bounded output signal. Though it is not absolute necessity, but your signal should be absolutely integratable. And what was the formula for absolute integrity? So it was integration minus infinity to infinity x of t is to minus delta t into dt must be less than infinity. So it should be finite. In short, my signal should be finite. And there is something called ROC, or the region of convergence. So the range of the values of my delta for which my Laplace transform is converging will be called region of convergence, or ROC. Okay, so what is happening? The range of various values of sigma, for which my Laplace transform is converging, will be called region of convergence, or ROC. Now this ROC is also having some properties of in its own. So the properties of ROC are mentioned here, that there will be no poles which will lie in ROC. So ROC will be poleless, or there will be no pole present inside of it. The second point is the ROC of causal signal is right hand sided. It is of the form of real value of s greater than value of a. So the ROC of my causal signal will be always right hand sided, and then the ROC of non causal signal will be always left handed sided, and it is for the form of real value of s less than a. And the last point, the system will only be stable if its ROC will include j omega axis of my s plane. These were the properties of my ROC. Now let's see what are the properties of my Laplace transform. Okay, so first is linearity. I'm not going to explain the linearity in detail because we discussed it in the very last lecture for Fourier transform. So the linearity of my Laplace transform is also very similar to the Fourier transform, so I'm not going to prove it one more time, but I'm going to show you the formula. Formula is given as a1, if you are a1 x1 of t plus a2 x2 of t is your input signal, then the Laplace transform of that signal will be a1 x1 of s plus a2 x2 of s. You can also do the time shifting same ways we did earlier. So for the time shift, you can say x of t minus t0. The Laplace of that will be e raised to minus st of 0 x of s, and its region of convergence will be r plus re of so or s0. Time scaling property will remain as it is. There will be there will be not a single change in time scaling property, so I'm not even going to mention it. The fifth one is the differentiation in time domain, and it is again basically same as the differentiation we used to do. So when we do the differentiation of your input signal in time domain, you will get sx of s uh, in the frequency domain. So what is this sx of s, right? What is this sn x of s? So that is the differentiation in my s domain, right? So whenever you differentiate something in the x domain, what you will get, let's say you are having a value of minus t and into x of t. So what will be the what will be the Laplace transform of it? It will be d by ds x of s, and we can do it for the other variables as well. Uh, we just need to make few adjustment. We need to make some very small changes and you are good to go. Then the next one we have is the convolution in the time domain, which means uh, if you are taking convolution of your two signals in time domain, so the output signals will also be uh, convolved in time domain, right? So basically x of x1 of s and x2 of s will be also uh, in convolution with each other. The next one is the integration, which is also same as we saw earlier. If you take integration of your signal x of tau into d tau with the limit of 0 to t, then the Laplace transform which you will get will be x of s divided by s, and its region of convergence will be uh, re of s greater than 0 and its intersection with r. And the rest of the properties we discussed earlier, they also have the intersection r for most of the cases except for the convolution. It will be r1 um, r1 intersect with r2. So that will be the region of convergence for convolution in time domain. Now integration in s domain. So same ways you can find the integration in s domain as well. If you are taking Laplace transform of your signal x of t divided by t, then what you can do, you can take 0 to infinity in an integral, and you can find the value of x of s into ds. And again, its region of convergence will also be the whole r plane. Then the periodic function, we just saw the Fourier transform of periodic function. Now for the Laplace transform of periodic function, again you will see the similarities here. The x of s will be equal to 1 by 1 minus e raised to minus st into x1 of s. After that, we are having, what are we having? Okay, we are having differentiation in time domain for unlatent Laplace transform. So when we take differentiation of my signal t and then we do perform the Laplace transform on it, what you will find? You will find x of 0 and you will find sx of s. So sx of s minus x of 0 will be the differentiation in the time domain for unilatent Laplace transform, and its region of convergence will also be 1. And then at last we are having two very important theories called initial value theorem and final value theorem. So in initial value theorem is given using this formula: x of 0 complement will be equal to limit t tends to 0 plus x of t. And after seeing that, we can find the value of um, we can find the value for them. So it will be limit s tends to infinity x of s. Then we are having the final value theorem, and it states that if we are having x of infinity, so you can take the limit of t tends to infinity s of t, and the output of it will be limit of uh, s tends to s tends to 0 s of xs. That is your final value theorem. So these are the properties of my Laplace transform. And the last two properties, initial value theorem and final value theorem, are very important. Whenever you will do the sums, you will be using them uh, very 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 widely. Okay, so we will keep today's class till here, and in the next time we will be completing the Fourier transform and inverse Fourier transform. So I will be seeing you in the next class. Thank you very much for listening, and take care of yourselves. If you have any doubts or queries, or if you have any feedback or suggestions, please feel free to mention them in the comment section below. I will try to answer them as quick as possible and as many as possible. Oh, all right. Thank you very much for listening, everyone.